Hello and welcome to my talk about the device tree, the order description for everybody. My name is Thomas Petazzoni and I have been working at Bootlin for over 12 years as the CTO and one of the embedded Linux engineers. We are a consulting company providing embedded Linux expertise such as development, consulting and training to our customers in fields like bootloader development, Linux kernel development, Yocto project and buildroot. We do complete Linux BSP development, hardware support in bootloader and Linux, and we have a strong open source focus with a lot of upstreaming work and contributions, and our training materials are all freely available. I am also one of the co-maintainers of buildroot and I live in Toulouse in the south of France. So this talk is an update from a talk I did many years ago called Device Tree for Dummies back in 2013-2014. And in this talk, we are going to discuss what is the device tree, why we have the device tree, what is the basic syntax of the device tree, the principle of inheritance that exists in the device tree, what are the specification and the notion of device tree binding, how do we build and validate device trees, and most importantly, what are the common properties and a number of examples about device trees. So this is a slide showing an example embedded platform which contains a system on chip in the middle in the gray box. This system on chip includes a number of CPU cores in blue and around it a number of peripherals such as GPIOs, Ethernet MAC, PCIe controller, GPU, DDR controllers and many others. This system on chip is then included into a board on which you have additional components such as a SPI flash, a touchscreen controller, a DDR memory, a camera sensor, a display panel, an audio codec, and more. And this typical embedded platform is important to keep in mind, as the reason for the device tree is to describe the hardware that we have in such platforms. In such platforms, we have some hardware that is discoverable and some hardware that is not. So we have hardware buses that provide discoverability mechanisms. For example, on PCIe or USB buses, you don't need to know ahead of time what devices are connected on those buses. The devices can indeed be enumerated and identified at runtime using mechanisms that are part of the definition of those buses. You have the concept of vendor ID, product ID, device class in PCI and USB, which allows to uniquely identify a device and therefore the corresponding driver that is needed in the operating system. But there are many more other hardware buses that do not provide any discoverability mechanism. For example, I2C, SPI, one-wire or memory map devices are typically not dynamically discoverable. One needs to know what is connected on those buses, how they are connected to the rest of the system. And embedded systems typically make a lot of use of such buses. Indeed, I2C, SPI, memory map devices are very common in most embedded systems. So the hardware description is necessary for this non-discoverable hardware. The operating system needs to somehow get the details for things like the system on chip has 2 Cortex-A9 CPU core, 2 UART controller of this specific variant with registered at that address, and the RQ line that one, and the other UART controller with this other address for the registers and this other interrupt line. That's the same system on chip as maybe 3 I2C controller of that other variant with register there and the interrupt line here and the input clock there. All those details the operating system simply cannot guess. This also applies to what is available at the board level. For example, let's say you have a Cirrus Logic 4234 codec. How can the operating system guess that it is connected on the I2C bus 0 at slave address 45, connected to the I2S interface 2 of the system on chip with the codecs providing the clocks, and that this codec has a reset signal connected to some GPIO of the system on chip? Again, all those details cannot be guessed by the operating system or the bootloader. They have somehow and need to be described either in code or some other data structure. So we have different possibilities to do that, to provide this description. It can be done directly in the operating system or bootloader code using compiled data structures, typically in C. And this is how it was done on most embedded platforms in Linux and U-Boot. But it was at some point considered not maintainable, sustainable, mainly on ARM32, which motivated for this specific architecture the move to another solution. Another solution that exists on some platforms is ACPI tables. This is the widely used solution on x86 systems, but it is also now available on a few ARM64 platforms. In this case, the ACPI tables are provided by the firmware, so on x86 systems it would be your BIOS, that provides those tables to the bootloader and to the operating system, and those tables describe the non-discoverable aspects of the hardware. Another solution, which is the main topic of the talk today, is the device tree. It is used on most embedded CPU architectures that run Linux, for example ARC, ARM64, RISC-V, ARM32, PowerPC, Xtensa, MIPS, and a bunch of others. It originates from the PowerPC world and is not a Linux-specific solution, but it is now used in Linux, in U-Boot, in Barebox, in the ARM Trusted Firmware or TFA, in FreeBSD, and perhaps in other projects as well. Writing and or tweaking a device tree is not always necessary when you want to port Linux to a new board or support new hardware on one of those CPU architectures. So the principle of the device tree is that you write as a developer a tree data structure that describes the hardware in a format called device tree source, typically stored with a .dts extension. This file that describes the hardware gets compiled to a more efficient representation called device tree blob or DTB, so the extension is .dtb, and this transformation from source to blob is done by the device tree compiler or Dtsi. The resulting DTB accurately describes the hardware platform in an OS agnostic way. And it can, for example, be linked directly inside a bootloader binary. This is what U-Boot or Barebox would do. Or it can be passed by the firmware or bootloader to the operating system, and this is what would happen with Linux. So for example, nowadays when you boot Linux on an ARM32-bit platform from the U-Boot bootloader, you use the bootz command, which takes the kernel address, where the kernel image has been loaded into RAM, and the device tree blob address. So the operating system really needs to have access to the device tree to be able to recognize what hardware is available and how it is organized. Here is a first look at the base syntax of the device tree. So on the right hand side of that slide, you can see an example of device tree with a number of comments. So it is really a tree of nodes that are separated by curly braces, a little bit like data structures in C. There is a root node that is labeled with slash, and a number of subnodes. For example, node at 0 is a node, node at 1 is another node at the same level as node 0, and child node at 0 is a subnode of node at 0. Each node has a name. In this case, node is a node name, child node is a node name, node is another node name. And then each of those nodes have properties, and they each have a name and a value. The property values can be strings, can be integers, can be arrays of integers, can be booleans, so there are different types of properties. And pretty much in the usage of that device tree syntax for representing hardware, we will have one node representing a device or an IP block in a system on chip, while the properties will be there to describe the characteristics of a certain device. It should be kept in mind that the device tree compiler, Dtsi, only does syntax checking, but no semantic validation. So Dtsi allows you to write completely arbitrary properties with completely arbitrary values. It only matters that the device tree is syntactically correct. So let's have a look at a simplified example of a device tree. On the right hand side, we have a very simple embedded system that has a system on chip with 2 Cortex A9 cores. It has a DDR controller, an I2C controller, a GIC interrupt controller, and a USB controller from the chip idea vendor. And on the left side, we see the device tree, which has been simplified a little bit with some nodes folded, and we will unfold them in the next slides. So we have a top level node, which really englobates all the other definitions. And it has a number of top level properties, address cells and size cells, which we will be discussing later. It has a compatible property, which identifies the platform as a whole, and we will again talk about the compatible property later. And then it has a number of subnodes. Some of those nodes are mandatory in the device tree specification, and some are really specific to each platform. The CPU's subnode is specified by the device tree spec, and it will contain description of the CPUs. Memory will describe the memory. Chosen will describe firmware-related information, and SoC in this case will describe the devices inside the system on chip. So let's have a look at those subnodes, and starting with the CPU subnode. So we have two CPU cores, so we have two subnodes, CPU at 0 and CPU at 1. Each of those nodes also has a label that you can see before the colon, CPU 0, CPU 1. These labels can later be used to refer to such nodes in other parts of the device tree. A little bit like you would have pointers in C. The device tree has a concept of p-handle, which allows one property to point to another node using this concept of label. So here we have two CPUs that contain in our system. The next node is the one describing the memory, so the RAM that is attached to our system. It's a very simple node which contains just a device type property saying this device is a memory, and a reg property that gives the base address of the memory, physical base address, and its size. The other subnode that we have expanded here is chosen, which is a mechanism that allows the firmware or bootloader to pass extra information to the operating system, which is not exactly hardware description. For example, the bootargs property will be used by the bootloader to pass the kernel command line to Linux. stdoutpass is another variable that can specify what should be the default output for the kernel messages. And then we have the SoC subnode, which is actually the most important one and where the biggest part of the device tree will be. This node, whose name can be different from one platform to the other, again, this one is not specified by the device tree specification, will be there to encapsulate all the devices that we have in our system on chip and the devices that are connected to them. So for example, here we have the description of an interrupt controller, which is our geek interrupt controller. So it has a number of properties that describe this interrupt controller, and we will discuss those properties later on. It describes an I2C controller, and this I2C controller is interesting because not only the I2C controller itself is described, but we have an EEPROM attached to this I2C controller at slave address 52. And this EEPROM, which is an I2C device, is described as a subnode of the I2C controller. So the device tree is a tree representation of the hardware that mimics the topology of the hardware. The EEPROM is connected to that I2C controller, so we represent the EEPROM as a subnode of that I2C controller. So if to this very I2C controller there was another I2C device, such as an audio codec for example, it would be also represented as a subnode of that I2C controller, just side by side with the EEPROM. Moving on, we have yet another device in our system on chip, which is a USB controller. And it is again described by a number of properties that we will discuss later on. But here you can see that no USB device is described as a subnode. Indeed, USB is one of those buses that provide dynamic enumeration. So in the vast majority of the cases, there are no need to describe USB devices in the device tree. The USB controller will be able to enumerate them and discover them at runtime. So where do you find these device tree sources? Even though they are completely, or at least supposedly, operating system agnostic, there is currently no central and operating system neutral place to host device tree sources and share them between projects. Indeed, as we've seen, they're already used by Linux, by U-Boot, by Barebox, by TFA, by FreeBSD, and perhaps other projects as well. But there's no neutral place to store them. So in practice, the Linux kernel source code can more or less be considered as the canonical location for device tree source files. So in Arch, ARM, or Arch ARM64, boot DTS, this is where you would find for each CPU architecture the device tree files. There are approximately 4,700 device tree files as of Linux 5.10, and this is obviously growing and growing as we add support for more system on chip and more platforms. Those device tree files for Linux are sometimes duplicated or synced in various other projects, and this is what U-Boot and Barebox are doing, for example. These device tree files are not monolithic. Instead of writing everything in one single DTS to describe your complete platform, we will typically split that into multiple files that can be reused between platforms. So we have the concept of Dtsi files, which are device tree source include files, which can then be included into DTS files. Only DTS files are accepted as an input to the device tree compiler, so only DTS files can really be compiled, but they can include any number of other DTSI files. So a very typical use case of this inheritance inclusion mechanism is that DTSI files will typically contain the definition of what is inside the system on chip, and then this DTSI describing the system on chip devices will be included in all the DTS files describing boards that use that system on chip. For example, for the TI AM335X system on chip, which is quite popular as being used for the BeagleBone platform, there is one DTSI file describing the system on chip, and all boards that use the AM335X system on chip will include the same DTSI and specify, in addition to what is described in that DTSI, the devices that are on their specific board. And this inclusion works by overlaying the tree of the DTS over the tree of the DTSI. And of course, this can go on with multiple levels. This inclusion is done with the C preprocessor directive sharp include, because all DTS files in Linux are passed through the C preprocessor before they are fed into the device tree compiler Dtsi. This most notably allows to use sharp defined definitions and provide like human readable constants instead of hard-coded values. So here is an example using the AM335X SoC as an example. So on the top left, you have the AM33XX DTSI, of course just a very short portion of it, which describes one UART controller. So it describes a UART controller with a compatible property, a reg property, an interrupt property, and a status property. You can see here that the status is disabled, which means that the device is not really used. And then on the top right, we have a DTS file, which describes a particular board that uses that SoC. It starts by including the DTSI, as I mentioned. And then this DTS is going to override or add additional properties to this serial port controller description. As you can see, the status is changed to be OK to indicate on this specific board the UART controller is actually used, so the device should be enabled by the operating system. And two additional properties, pin control names and pin control 0, are also added. At the bottom of the slide, you have what looks like the final DTB. Of course, in practice, the DTB is binary format, so it doesn't look like text file, but this is what you would get if you would decompile the DTB back into a source file. So what you see is really the combination of the DTSI plus the DTS, where the values specified in DTS win over the ones defined in the DTSI. When you do such inheritance, you have two ways to override values specified by a DTSI. You can either do like the example shown, replicate the hierarchy of nodes and at the same location define a property with the same name. So for example, in the case specified here at the left bottom, you would get the status be OK in the final DTB. But another way of doing that is to use the label. And on this example, the serial node has a label called UART0. So you can replace this solution by the one on the right side, where in the DTS, instead of having to replicate the hierarchy all the way down to the specific node you're interested in, you can use this %UART0 notation and just override that status property. This solution is actually now the preferred solution at least in the Linux kernel for overriding properties from another DTSI you are including. How do you build device tree files? You typically don't build them manually. On ARM and ARM64, there are makefiles in the kernel that indicate which device trees should be built depending on the platforms that are enabled in your kernel configuration. So for example, Arch, ARM64, Boot, DTS, Marvel makefile is enabling several device trees, and this is just a small part of that file, which says that if config arc mvebu is enabled in your kernel configuration, this is one of the options for Marvel platforms, then the two device trees described there will be compiled. So you will get, as the result of the kernel build, two DTBs corresponding to those two hardware platforms. So if you run make to build your kernel, you would get those DTBs, but there is also an explicit make DTBs target that is available if you want to build just the DTBs. And during the kernel build, you would get messages like Dtsi and the name of the DTB, just like you can see the kernel building C files and sometimes assembly files as well. There is some work that has been done to validate device tree files. As I mentioned, Dtsi is only doing syntactic validation, but we now have some YAML written specification of device tree, and this is a topic we're going to discuss later in this talk, that allows to do semantic validation. And the Linux kernel has two new or relatively new targets in its build system to help with that validation process. Make Dtsi bindings check can verify that the YAML bindings are valid, that the YAML files can be parsed properly. While make DTBs check, we really check the DTS files that are in the kernel against all or one of the YAML binding that you can specify as an argument. And this is a very useful tool because the fact that Dtsi has only been doing syntactic validation has caused many people to lose hours and hours looking for issues in their device trees and ended up finding that it was just a small typo in a property name or just a mix-up in the values of the properties. And having validation at the semantic level allows to detect such silly mistakes and hopefully fix them earlier. When you have booted a system or Linux kernel with the device tree, you can also explore at runtime the device tree on the target, simply to verify if you're running with the right device tree, if it has the latest changes you have made. So if you go in the sysfs file system in /sys/firmware/device tree, you can explore the device tree where each node of the device tree is a directory and each property is a file. So you can cat all the properties, you can cd into the nodes and really check what your device tree contains. Very useful debugging tool. It is also possible to modify the device tree at runtime. Normally the device tree is just loaded by the bootloader and passed as is to the kernel, but in practice a few changes can be done or potentially more changes can be done. U-Boot automatically patches the device tree blob that is passed to Linux. First, to set the RAM base address and size. If you remember this memory top level node that we have in the device tree, you might have a default value in the DTS file you write, but in fact U-Boot is going to override that with the exact RAM base address and size it has detected. U-Boot can also pass the kernel command line to Linux using the /chosen/bootargs property that we have also discussed earlier, but it can also do other things like set the MAC address for network interfaces, for example. There are additional device tree blob patching features that you can do in U-Boot. There is a set of FDT commands, and FDT stands for flattened device tree. This is basically the compiled device tree format, which U-Boot can modify with commands like fdt set, fdt mknode, fdt rm, and there's a whole bunch of other FDT commands as well. Another concept is the one of device tree overlays, on which I'm going to spend a little bit more time. And the device tree overlays are there to solve a specific use case of platforms that have some flexibility aspects that are difficult to describe in a static device tree. Typically, a use case are baseboards that to which can be connected an arbitrary number of expansion boards. For example, in the BeagleBoard world, there are capes. You can connect expansion boards to your BeagleBone. Raspberry Pi hats also of the same concept. But another use case are FPGAs that contain arbitrary IP blocks that can be synthesized. And so this gives some flexibility into the hardware, which has to be reflected in the description of that hardware in the device tree. And to support that, instead of writing another device tree for each of these combinations that exist between a baseboard and any number of expansion board that you connect to it, the concept of device tree overlay allows to describe what is in your FPGA or what is in one of those expansion boards and have this device tree overlay be applied to a base device tree at boot time, a little bit like a patch to the device tree. So for example, such an overlay can describe a display panel that is on your expansion board, or a bunch of relays that are on your expansion board, or any other device that your expansion board contains. And the description of that device or devices will be added to the base device tree. U-Boot has support for applying device tree overlays, so it can be done in U-Boot before handing over the device tree to the kernel. There is, however, no support in Linux for applying device tree overlays at runtime. If you want to see some examples of device tree overlays, you can look at the Linux kernel tree for the Raspberry Pi project. This is where they store their overlays. So how does one know how to write the correct nodes and properties to describe a given hardware platform? Indeed, we have seen the overall syntax, then we've seen how the device tree gets compiled, passed to the operating system, but really if you need to write your own device tree for your own platform, how do you do that? How do you know what to write? There's really two layers of documentation that are available. The first base layer is the device tree specification, which is available on devicetree.org. And it provides the base device tree syntax definition and specifies a number of standard properties. For example, the CPU's node, the memory node, the chosen node, and a few other aspects are described in that specification. But it is far from sufficient to describe the wide variety of hardware devices we have today. So in addition to that, we have the concept of device tree bindings, which are documents that each describe how a particular piece of hardware should be described in the device tree. They are currently located, a little bit like the device tree files themselves, in the Linux kernel sources, in documentation /device tree /bindings. In theory, they are operating system agnostic, so they really have no place in the Linux kernel source code, but this is where they belong today. These bindings, which are documents, they are reviewed by the Dtsi binding maintainer team of the Linux kernel, which ensure that bindings across different types of devices are reasonably consistent and that people don't come up with creative ideas on how to solve the same problems. There are two ways of writing such device tree binding documents. The legacy way, which are simple human-readable text documents, but the new norm is to write them in YAML so that they can be used for device tree validation, as we have mentioned earlier. So here is an example of a legacy old-style device tree binding document, which is there to describe the I2C controller used in Atmel no microchip platforms. And it says that if you want to describe in a device tree an I2C controller for those platforms, you need to create a node, which has a number of required properties: compatible, reg, interrupts, address cells, size cells, and clocks. And then in addition, you can have optional properties. They can be there or they may not be there, such as clock frequency, DMAs, DMA names, SCL GPIOs, SDN GPIOs, and there are actually a number of others that I have cut just to make things fit on the slide. And then on the right column, such device tree bindings typically come with an example showing how it can be used, and you can see them in use. So we again see this principle where we have one node describing the I2C controller, and then as subnodes, we have the description of the devices connected to that I2C bus. Of course, the device tree binding for those devices is another device tree binding document because those are other devices. The new format in YAML is somewhat a little bit less readable as a human, but the benefit is that it is more easily machine parsable for validation. And this document specifies how to write a device tree to describe the I2C controller of AM logic SoCs. So it contains pretty much the same information, such as which properties are expected, which one are required. So we can see the required field says that compatible, reg, interrupts, and clocks are mandatory. And we can see that compatible can be one of those two values, that there must be one entry in the reg property, there must be one entry in the interrupt property, there must be at least one entry in clocks. And then there is an example again that shows how it should be used. There are some principles in the design of those bindings. The bindings should describe the hardware, like how the hardware factually is, but not the configuration of the hardware, like not how you personally choose to use the hardware. That is quite a bit of a distinction that they enforce when designing the device tree bindings. Also, the bindings should be operating system agnostic, which means that for a given piece of hardware, the device tree should ideally be the same for U-Boot, for FreeBSD, for Linux. So we really need to describe the hardware, and not how it is used by a particular operating system. And also, there should be no need to change the device tree when updating the operating system. There is a backward compatibility requirement that they try to enforce. In practice, it is quite difficult to always enforce, but they try to enforce it so that when there are changes that are needed in device tree bindings, they should be backward compatible. Also, the device tree should describe the integration of the hardware components, but not the internals of hardware component details. So for example, the details of how a specific device or IP block is working internally does not belong to the device tree. What belongs to the device tree is the description of I have an IP block there, which is an I2C controller, and then how it is integrated with the rest of the system around it. It is integrated with the rest of the system as being located at that address for its I/O registers. It is connected to this line of the interrupt controller. It is connected to this line of the DMA controller, and so on. And same for devices outside of the system on chip. If you have an audio codec, you are not going to describe the internals of the audio codec, but just like the external signals that's connected to the rest of the system. It's data interface for audio, it's control interface to the processor, maybe it's reset signal and other signals that it might have. Of course, like all beautiful design principles, the principles that I have just described are sometimes violated just because it is difficult to get them applied in all situations, or also because the device tree has a history. And in the initial steps of device tree usage on ARM, some mistakes were made, which are somewhat still present in parts of the kernel. So now let's have a look at a number of the properties in the device tree. And the most important property by far to explain is the compatible property. The compatible property is a list of strings from the most specific to the less specific. And this compatible property describes the specific binding to which the node complies. So this is the property that is going to say this node is describing this particular device using that specific device tree binding. And it uniquely identifies the programming model of the device. And this term programming model comes from the device tree specification. So essentially it means that if there is a given IP block, such as an I2C controller, which is reused between system on chips, we would typically have the same driver in the kernel for it, because it's in the same device tree representation, because its programming model, which means its list of registers and the meaning of the bits in those registers, is the same. It's the same IP block. So we can reuse the same driver, but also reuse the same device tree representation for it. So practically speaking, this compatible string not only just says which device tree binding is used to represent that device, but it is also used by the operating system to find the appropriate driver for that device. So it is kind of a free-form string, which for real hardware matches vendor, model, as you can see in the examples below, such as ARM, ARM v8 timer, or actions, S900-UART for a UART controller, would be compatible values for real hardware. The last two are for Linux kernel drivers, for regulators, fixed regulators, and for keys over GPIOs, which are not like real hardware, is more like what you do based on a given piece of hardware. There is also a special value that can be used for some compatible string called simple bus. This is the value that is used for a node in the device tree, which represent a bus where all sub-nodes are devices that are memory mapped. So it is very common that one of the top-level nodes describing all the devices in your system on chip will use that compatible value. In terms of association with the Linux kernel drivers, this is how it gets done. For example, for memory map devices. In Linux, memory map devices are managed by what we call platform drivers, and each of those platform drivers registers in the Linux kernel a struct platform driver that you can see here at the bottom of the slide. This structure contains a number of function pointers such as probe and remove, but one of the things that matters to our discussion is the ID table field. It points here to a structure called IMX UART Dtsi IDs, which contains the list of compatible strings that this driver is capable of supporting. And as you can see in this driver, each compatible string is associated to a data field that I had to cut off for size reasons, for space reasons, but that is different for each compatible string. Indeed, this very driver, which is a driver for the IMX UART controllers, is supporting 4 different types of UART controllers, all coming from Freescale, but they have some small variations. They are not sufficient to warrant making different drivers for each, but still the driver needs to know whether it is an IMX6Q type of UART, an IMX53 type of UART, an IMX1 type of UART, or an IMX21 type of UART. And the compatible string will indicate that, associated to a different data value that the rest of the driver can use to act slightly differently depending on the type of the UART. Besides this compatible property that mainly identifies the driver, we have a number of other important properties that are commonly used. The reg property has different meanings depending on the device that uses it. If it is used to describe a memory mapped device, the reg property provides the base address and the size of the I/O registers to communicate with that device over the memory mapped bus. There can also be several entries if the device has multiple areas of registers. For I2C devices, the reg property will contain the address of the device on the I2C bus. For SPI devices, it contains the chip select number, and every bus can give a slightly different meaning to the reg property. Then we have properties to describe interrupts. Interrupts will give the interrupt number and sometimes a bunch of flags related to it. Interrupt parent will point to the interrupt controller that is used for all the sub-nodes in the device tree, while interrupts extended can provide bus at the same time. So it's a single property that allows you to give a pointer to the interrupt controller and the number of the interrupt that you want to use from that interrupt controller, as well as a number of flags. Clocks is also widely used. It indicates which clock or clocks are used by the device that you are currently describing and from which clock controller. DMAs, in a similar way, will describe which DMA controller your device is attached to and which channel of this DMA controller it is using. Status, that we have already mentioned before, indicates whether the device should really be enabled or not by the system. So a status of OK means that the device is present and should be enabled by the operating system. Any other value would leave the device unused, almost as if it was not even described in the device tree. There are also pin control properties that describe the pin muxing requested by that device. In the device tree, there is a concept of cell to encode integer values. So all integer values are encoded in 32-bit values, which are called cells. So the example here of the property foo is a property that has a value of just one cell. If you want to encode 64-bit values, you need 2 cells of 32-bit. So in the new example, foo is a property with 2 cells of each 32-bit forming a 64-bit value. And then we have properties such as sharp address cells and sharp size cells that indicate how many cells are used in the subnodes to encode the address and size in the reg property. So first of all, let me make it clear. They start with sharp. They are not comments. Even my syntax highlighting gets it a bit wrong. They are in green because they are considered as comments, but they are not comments. They are really just properties whose names start with a sharp sign. So if we look at this SOC node, it says compatible equals simple bus, which again says every sub node describes a memory mapped device. One of the memory mapped devices that we have is an I2C controller. But this SOC node also provides 2 properties for the number of address cells, 1, and the number of size cells, 1, that are used by the reg properties of the child nodes. So the reg property of our I2C controller has 1 cell for the address, which is F1001000, and 1 cell for the size, which is 1000. So this is the base address of the memory map register for the I2C controller and the size of the register area. But then this I2C controller node itself overrides those values and says for the subnodes of me, the number of cells to encode the address will be 1, and the number of cells to encode the size will be 0. And indeed, in the child node, which is an I2C EEPROM, we have a reg property which contains just 52, just 1 cell, which encodes the address. And indeed, for I2C devices, they are not memory mapped. We don't have a notion of address and size. We have just an address, which is the slave address on the I2C bus. So we need just 1 address cells and 0 size cell. This concept of cells applies to other things as well. For example, sharp interrupt cells is a property that is defined by a node in the device tree describing an interrupt controller. So in the example here, the first node in C describes an interrupt controller in your system on chip. And it says #intro cells equal to, which means that any device, such as the I2C controller described below, which says my interrupt controller is int C, and here we see an example of using a label to point to another node in the device tree. This pointer, &int C, is called a p handle, and this is very common in the device tree syntax. And then the interrupts property must have two cells, here just arbitrary example 12, 24, because the target of the p handle, which is our interrupt controller, has specified I need two cells in my interrupt specifiers. And this is because the interrupt controller driver will parse these two values, 12, 24, to find which interrupt is actually used by our I2C controller. And this goes on and on for #clock cells, #GPIO cells, #phi cells, #PWM cells, #DMA cells, and so on and so forth. So here is an example again with our I2C controller, which has a clocks property pointing with a p handle to a clock controller, identified by the CLKC label. And this clock controller has #clock cells 3, which means that it needs 3 additional cells to describe which clock is actually going to be used, and perhaps with some flags. Here we have just put some arbitrary value for the example, and the values are 12, 24, 32, which are those 3 cells used to identify which clock from that controller we need to use for this I2C controller. Another very common pattern in the device tree is the usage of -names properties. For example, here you can see an interrupts property and associated to it an interrupt names property. And the interrupts property has 2 entries. The first one is 0590 and the second one is 070. And the interrupt names property also has 2 entries, MAC-RQ and MAC-PMT. And those names can then be used by drivers to more easily identify which interrupt is what in the list of interrupt specifiers. So for example, the driver could do something like platform get RQ by name and ask what is the RQ called MAC-RQ. And the device tree logic in the kernel would automatically find it is 0590. There is another example with clocks, which follows exactly the same rule. And this is again something we can find for many other properties, reg names, GPIO names, and so on and so on. So this kind of concludes our visit of the device tree as a way of representing non-discoverable hardware. It is, as we've seen, a tree of nodes with nodes having properties. There is a standardization of how to describe a specific piece of hardware based on the device tree bindings. The device tree is a new description language which has lots of properties, and sometimes the bindings are complex. But it is now used for numerous CPU architectures, widely used in Linux and outside of Linux as well, and it has definitely become a must-know for all embedded Linux developers. I hope this talk will have helped you understand device tree, and if that's not sufficient, do not hesitate to contact me.